What we're going to do is we're going to talk about pointers more in the way that they are very often used, which is to contain the address of a structure that you allocate. And we've already talked about structures, but usually we've only created one structure. And if we needed a second structure, we would have created a second variable. And need a third structure, a third variable. It's not really how they are usually used. There is a function called Malloc Memory Alloc, which asks the computer for a block of memory so that you can use it. Let's get Visual Studio going. And then once you have that block of memory, you can store data in it. And you can malloc anything. You can malloc an array, you can malloc a structure, you can malloc an array of structures. We're going to malloc a structure, and then we're going to malloc an array of structures. Grab the good old boilerplate. Looks like we're on lecture N. And we may be out early. This only takes 30 minutes to cover or something. We'll see. I'm not going to talk just for the joy of hearing my voice. Something specific I want to cover. Alrighty. To force it to actually compile it in C mode rather than C++ mode. I haven't been really making y'all do this. Maybe you've caught me doing it. Is to change the extension to .c rather than .cpp, because the rules for a .cpp file are different than a .c file. And by and large, backwards compatible, so you can put C code in a CPP file and it doesn't care. But doing it like that kind of forces it to be a little bit more strict in how it compiles. Yes, sir?
I was wondering if we could take my test right now.
Oh, yeah, come on.
Okay.
Yeah. All right, we need a structure to play with, something to store some data in. I don't know. How about a rectangle that has a height and a width? So we're going to use struct, and I'm going to call it rect with a capital R. One school of thought is that if your structures and your classes begin with a capital letter, it's easier to pick them out when you're looking at the code. I put some parentheses there and they were not correct. Curly brace, and then inside the curly braces I need to list the pieces of data that rect contains, which could be a height and a width, right? So int height, or I could just make it age, int width. So the way a rectangle works is you can create a rectangle like this, rect space R1, and then R1.height equals whatever, 10, R1.width equals 20, and then we could do something with those numbers. And I seem to have made a mistake. Wonder what? Rect is undefined. Well, it's right there. Maybe I just need to compile and the error will go away. Expected a semicolon. Well, I have a semicolon. Have we not used structures yet? Is this the first time we've seen that keyword?
Yeah. Do we need to include?
No, we don't need to include anything. But maybe it's only in C++ that you can create an object like that. Maybe in C we just have to flat out malloc it right off the bat. If that is the case, here's what we're going to do. We need to know the size of the structure in order to malloc it correctly. Malloc just stands for memory allocate. We're going to ask the computer to give us a certain number of bytes in memory so that we can store structure. To do that, this can't just be a variable of that type, it has to be a pointer of that type. See if that makes our errors go away. Rect is not undefined. What is your problem?
Oh, you have a semicolon at the end of your struct, right?
I do, because that is actually required. Now, I had code like this working downstairs just minutes ago, so I'm astonished that it's not working now. What is your problem? Okay, this is stupid. Pause the recording. Alrighty then. In this language, we have to prefix the word struct here with what it is. It is, in fact, a struct. Yes, sir? Let me come look. Alrighty, which brings up a point. There's something called type def, which we have not been doing. Type def is when you want to create your own type so it'll work like a keyword. We could create a type def which stands for struct rec. Let's go ahead and look at the syntax for a type def. Type def in C. What we could do is we could say that if I ever want to use an unsigned character, I could call it a byte. And that makes it a keyword, right? And then I could create 2 bytes, and they would actually be unsigned chars. So if I wanted to, this would be stupid and I wouldn't, but type def, you know, and if I wanted to call a long int a big num, then down here I can make a big num, you know, b1 comma b2 comma b3. All it does is kind of let me set it up so that if I use that word, the compiler substitutes that word for it. Well, I could do the same thing here. Make that a lowercase r right there for struct rec, but then we're going to type def struct rec, rect with a capital R. And now we don't need that big num really. I'm going to delete that example. Now we don't need to add the word struct in front of it. That works just as well. That kind of duplicates the way you would see it in Java. Except in Java you wouldn't use a pointer, but that's okay. So if I go back to what I was originally trying to do, oh, and by the way, you don't have to do that. It would be totally fine just to go ahead and do struct rect like that. You don't have to do a type def in order to use structures. It just makes the syntax a little bit cleaner. You get to leave the word off there, but who cares, right? It works. You do not have to put that keyword there in C++. Probably wouldn't break it, but okay. Anyways, what was I trying to do? I was trying to create a variable of type struct, right? There we go. Or I could call it rect with a capital R because I have a type def for that. And then I can say R1. See, it has 2 members here. R1.height. Come on. R1.height equals 10. R1.width equals 20. And then, you know, I could calculate the area as being the width times the height. We might want to write a function that would calculate the area so that we could pass a rectangle to it and it would return the area. Something like this. Since those are ints, we may as well make the function an int. Int calc underscore area parentheses. And it's going to take a rect, and I'm just going to call it rect parameter r. And it could return r dot height times r dot width. So if I wanted the area of that rectangle, I could do int A1 or whatever area, I'm going to just say A1, equals calc underscore area, and then pass in that rectangle, R1, like that. And now I have the area and I can print it out or something like that. When you're dealing with structures, it's better to pass the object in by its pointer rather than by its value, because if we pass it in by its value, it has to copy it in byte by byte. This thing actually has more, than one piece of data in it. It could have hundreds of pieces of data in it. It could have an array full of 7,000 pieces of data. We would not want to have to pass in or make the computer pass in all 7,000 bytes every time we call this function. If we pass it in by pointer, all it does is pass it in just with an 8-byte value that contains the address. And like I've mentioned in the past, if you have the address of something, then you can access it, or the compiler can, by using that address. Just like if I give you my home address, then you can go to my house. So we're going to change this so that it accepts a pointer. And I'm putting a P there because in general I think it's a good idea that if you're using a pointer, sticking a P in front of the variable name is a good way to remember what you're doing. But now these references are broken. And if you're using a pointer, you don't use this dot reference. You use something that you're not going to see in Java. You do see the dot syntax all over the place. So we're going to do PR hyphen greater than height asterisk PR hyphen greater than width semicolon. And what this means is using this address, go to that memory location at PR and then find the height and the width members of that structure. But when we call it, we have to pass it in by its address, because that's what a pointer is expecting. It's expecting an address. So I'm going to stick an ampersand here just to indicate that we're passing in as a pointer. And I guess we ought to print the area out, right? Printf parentheses quote area of R1 is %d \n comma A1, just so we can make sure it works, right? If it's a 10 by 20, I want to say CSA200. And by the way, this is not necessary, this R1. It just happened to create a variable with that name. You can create a variable right as you create the structure, but we don't want that. I'm going to delete that up there. So if you added that to your structure when I did, get rid of it. All right. So now we know how to use a structure. We can declare a structure that contains any kind of data. It can contain floats and longs and arrays and all sorts of things. So it's a way of moving not just one variable around, but a bunch of pieces of data around. It could have arrays for your name, your first name, your last name, your address, your birth date, your height and your weight, right? If we were doing some medical application, or if it was a library, book title and print, publishing house and the author and the version and how many pages it is and whether it's checked out or not. You can cluster all that data so that it can be referenced by a single variable name. Since we have this right here, we can carry these two pieces of data around under one variable name, R1, and we could pass that one variable in, and it actually has access to both pieces of data. And if we kept expanding this, if it was no longer a rect, if it was a three-dimensional block, we could add another variable for that, right? We could add int height, width, and depth, or whatever it needed to be. Okay, so that is how you create a variable from a structure. Let's make some notes. Create an object from the rect structure or of type rect, which is a structure. Note we are using a type def so we don't have to put the word struct in front of the variable definition. And we could create we could play with creating more structures just to get the idea, but I think that's enough. Now let's go and add a comment to this one. Calculate the area of the rectangle pointed to by PR. PR is a pointer to a rect structure. That's what the asterisk means, is it means it's a pointer rather than the object itself. You know, if we tacked on more ints, each one of these is 4 ints. If we had, 8 one of these, we'd have a structure that was at least 36 bytes long, right? Because 36 times 4 per int, 8 times 4 per int is 36. So when it was invoking it, if we had not made it passive by pointer, it would have to copy in 36 bytes on the call stack as the argument got pushed into the parameter variable there. But passing it in by address, each address is only 8 bytes long. So that works just great. It's speedier, less memory gets copied around, and if it had to, it could actually change these values. If we wanted to reset height and width to 0 inside of some function, passing it in as a pointer lets us do that. Alright, so that's one way of doing it. But now we're going to use Malloc to allocate a structure. What Malloc does is it tells the computer, yo, I need the right number of bytes to create one of these things. And so it's not allocated as soon as the program loads, which this one is. Instead, it's allocated at runtime as the program is running and as it needs it. But to do that, we're going to need a pointer to a rectangle. The reason we need a pointer to it is because that's what Malloc returns. It returns the address of the bytes that it just asks the computer for. So rect asterisk PR2. This is a pointer to a rectangle. Now let's tell the computer that we want enough memory to hold a rectangle. So PR2 equals Malloc, parentheses in parentheses, and we have to tell it how many bytes a rectangle is. Well, the fastest way to find that out is to use size of. Size of a rect, like that. Or maybe rect with a capital R to make it match our other syntax, and 2 closing parentheses. It'd be interesting to print out the size of the rect. I believe it's 8 bytes because it's got 2 ints in it. We could print it out if we wanted to. But now, PR2 is a pointer to a block of memory. And we could set its X and its Y values if we wanted to. Just like we use the syntax up here, where we did the hyphen greater than to access those points. We're not going to use dots because now we have a pointer. We have the address. This is a way of indicating to the compiler, oh, this isn't a variable, it's an address to a variable. So PR2 hyphen greater than height equals, well, I don't know, this is going to be 100 by 100. Equals 100, and then PR2 hyphen greater than width equals 200. And again, we could get the area of it if we so chose. It's already a pointer, so we don't need to use this ampersand now. We could just do A1 or int A2 equals calc underscore area, and like I said, since it's a pointer, we don't need to use the ampersand, so PR2. And if we felt like it, we could print that out as well. Why not? I'm just going to copy that printf statement and change those 1s into 2s. So area of PR2 is A2. The only thing about Malloc that you need to take care of, and you really, really, really need to take care of it if it's a complex program and not just a little demo like this, is that the memory has to be freed when you're done using it. What does that mean? Well, if my program asks for a megabyte of data and it never frees it, and then it turns around and it asks for another megabyte and another megabyte and another megabyte, and it never releases any of it, then you can run your program out of memory. Right? It's like you keep, renting rooms from a hotel, and so you allocate, a room, you rent that room, but you don't go out of it, you don't, move out of it. Instead, you allocate another room, you move into that room, and you move into the next room, and you move into the next room. You keep doing that without ever moving out. You eventually would go, have used up every room in the motel. I don't know if that makes any sense, but it is a truism. When you malloc, you must free the memory when the program is done with it. If you do not, it will cause what is known a memory leak. A memory leak is a program that asks for data and never releases it. Like each time you go to school, you grab a new shirt out of your closet, you never wash them. Eventually you run out of clothes. You have to do something to make it so that it's ready for you to use the next time. The Firefox browser used to be notorious for memory leaks. If you ran Firefox and you never shut it down, people don't reboot their computers regularly anymore. So you let Firefox sit there for a couple of days or two. You'd come back, and if you checked how much memory it was using, it'd be using an astronomical amount because it would allocate RAM and it would never free it. Now, languages like Java and Python don't have to worry about that because they don't have the malloc keyword. They don't have pointers. And they have something called garbage collection. Garbage collection goes and frees up that memory as soon as the object is no longer needed. Now, it's not exact. It's not like it disappears the very nanosecond it stopped being needed, but the garbage collector comes along, and if it notices that there's some memory that's no longer being used, it goes ahead and frees it. So the programmer doesn't have to do that. And in fact, in those languages, the programmer has no control of when that memory is freed because Python or Java are taking care of it for you. In C, nothing gets taken care of for you. So if we allocate it, we got to free it. Why don't we put a comment here as to what this is doing? Underneath the malloc, I'm saying malloc equals memory allocation ... ask the operating system for a certain number of bytes. You could use that to hold a string if you needed a lot of string space. If you were going to, read in a book and you knew that, the book, each sentence could be, up to 1,000 characters long or not. That might look like this. What is a string? It's an array of characters. So char star PCH equals malloc parentheses. Let's get the size of a character. So size of parentheses char in parentheses times 80. Now we have a string that can hold 80 characters, or 79. There are certainly other ways of doing it. We've already learned one way, which is just to do this. Char PCH, char CH2, something like that, 80. Those do the exact same thing, honestly. Those do the exact same thing. Now, why would you want to do it like this? You would only want to do it like this if you need to keep allocating new strings. Like if you're inside some function and every time the function is called, it needs to add whatever was sent to it to some kind of array or something like that. So normally you're not going to need to do this, but it kind of shows the idea. We're asking the computer, the operating system, I want enough space to hold 80 characters. And so it allocates it and it stores it in that address. And if we wanted to, we could copy something into it. Right. str copy parentheses pch comma hello end quote in parentheses whatever. And if we felt like printing it out, we could. Or if we felt like using scanf to read something into that string, it'd work the same way, whether we use pch or ch2. Again, once our program is done with that memory, we should free it. Oh, I never freed it. I never freed this one. So I'm going to come back up here, and above that comment about when you malloc, you must free the memory, free, parentheses, PR2. That means go to that memory address and release it so the operating system can use it for something else. So we're not hogging it up. Same business down here. Let's free PCH. We don't need it anymore. Free, parentheses, PCH, in parentheses, semicolon. Alright, now let's say we needed an array to contain 100 rectangles. We were going to add up the areas of all of those rectangles, or something like that. We can do that. We have to create an array of pointers, though. And each pointer will point to a rectangle that gets malloced. Well, what's an array of pointers look like? Well, for one thing, I'm going to look at my notes to make sure I don't get it wrong. Alrighty. Just like every other array, just like we should have done here, we should store the array size in a constant. # define num underscore rex, stick the T there if you want, 80, no equal sign, no semicolon. Make sure you spell define right and not defubi, define. Alright, now we could create an array of 80 rectangles. 80 may be a bit too much. Why don't we just create an array of 10 rectangles? And here's what our array is going to look like. It's an array of rects. So rect space, I'm just going to call it array, subscript, capital NUM underscore rex. But it's not an array of rectangles. It's just an array of pointers. Actually, it is an array of rectangles. My mistake. I want to make it an array of pointers. So I'm going to have to come up here, and after the data type, before the variable name, I'm going to have to do that. Now let's print out the values of that array. We're going to find out that they just point to random positions in memory. Just whatever memory happened to be there when the array was allocated. You would want to initialize them to 0, to null, or to actually malloc each individual rectangle before you start using the array. So let's just find out what it looks like. Let's just take a peek. So for, parentheses, int x equals 0, semicolon, x is less than capital NUM underscore RECS, semicolon, x plus plus, and let's print out every element in the array. Printf, parentheses, quote, %p, because we're going to be formatting the values as addresses. %p means print it out as a pointer, so it's going to have letters and numbers in it. It's going to be hexadecimal. \n. But let's also print out the array member itself. So %d space %p. Comma, and so the index value, the subscript, is going to be x. And then we want that actual value, array subscript x. Let's print it out. And there we go. All full of C's. That's because it's compiled for debug mode. If I change this to compile and release mode, it would not be all C's, but it still would not be good data. Right? Just random data. Whatever happened to be in those bytes before the array was allocated, they're now there. It would be real bad news to try to write some height and width to those memory addresses, because our program probably does not own those memory addresses. And the operating system would pick up the fact that we were writing to memory we didn't own, and it would probably close the program. So we need to allocate 10 rectangles and store their addresses inside this array. Let's do that. We're going to need another for loop. There's nothing wrong with just copying that for loop and pasting it. Save ourselves a little bit of typing time. And we're going to say array subscript x equals, and this is going to give me a syntax error, which probably it was downstairs, but I was using a different compiler. I was using a Linux compiler. Malloc parentheses size of parentheses rect, the rectangle structure. So you see what it's doing, just like if we had one that was going through and putting random numbers into an array or storing sequential numbers or whatever, we're allocating rectangles. And we're storing the addresses of those rectangles into the array so that we can store data into it. So we can hold 50 different, or well, 10. You know, we could make that number as large as we wanted to. 10 different rectangles using one variable. Why don't we print those values out again? So I'm just going to copy that for loop, and I better walk around and make sure y'all are doing okay. There. So I just copied that printing loop and pasted it. And as a matter of fact, I'm going to remove some of these opening and closing braces just to tidy up my screen a little. You don't have to do that, but I like the way it looks. And there it went. We can see that each one was malloced. Now notice that the mallocs aren't all in order. We can kind of tell that it just went out and randomly, the operating system just randomly gave us little blocks of memory, and they didn't have to be in order. They kind of look like they're in order down here once we get to this point, but they're not in order up here. But that's okay. It's still a rectangle. We can still store pieces of data in it. Let's do that. Let's store some height and widths in these rectangles. Now for this one, I actually am going to need the curly braces. So I'm going to copy my for loop one more time. And we want to change the height and the width of that value. So again, we're going to use that hyphen greater than syntax. Array subscript x hyphen greater than height equals, I don't know, how about x times 10? So it'll be like, you know, 0, 10, 20, 30, 40, 50, and so on for the height. And array subscript x hyphen greater than width equals x times 20, right? 20, 40, 60, 80, 100. Now if we print the addresses out, we're just going to see the same data. This is not changing the addresses. Just like if I ask you to go and paint my house red, it's still the same address. So now that I want to print out the height and the width, I'm going to have to use a different syntax than this, because this is just the address. That contains a pointer. I don't want the pointer. I'm going to be accessing them like that. So one more print loop. I'm going to copy my for statement yet again. And I'm going to print f, parentheses, quote, rect %d which one we're on, 0, 1, 2, 3, 4, 5, 6. Height equals %d. Width equals %d. \n. And I'm going to go to the next line. You don't need to. But after the end quote, before the closing parentheses, I'm going to put a comma. So \n, end quote, comma. And which rect is it? What's our subscript? X. How do we get that address out and access it? Array subscript X hyphen greater than height, not semicolon, comma, array subscript X in subscript hyphen greater than width. And then I need my closing parentheses and a semicolon. So I'm going to go back and write a summary in a minute, but this is getting pretty close to being what I wanted to cover for today. I saw a few warnings pop up. It'd be interesting to go and look at them. View error list. Okay, unreferenced variable. Sure. To me, to get it to compile without warning, when I was using GCC, the Linux compiler I was using at the time, when I malloced it, I actually had to use casting to make it know that it was a pointer to a rect. I had to come up here and do this on that malloc statement. Rect asterisk. That said, take whatever it returns and format it into the format of a pointer to a rect. And I don't want to go too crazy on this, but you remember where we did that type def? Quite often you will see people do another type def, which is to define a pointer to the rectangle. Where'd that go? Where's my type def? Oh, it's above calc area. Yeah. Type def rect asterisk space p rect, a pointer to a rect. And then everywhere down here that I used rect asterisk, like I did when I was casting it, right there, I could substitute prect instead. Or when I was doing this, I could call it prect. Now I'm going to make the changes, but then I'm going to undo it just so that you can recognize it. Like that. Except I have a mistake. Maybe it was P with a capital. Lowercase p, capital R. I'm not sure why I did that, but anyways. Yeah, so lowercase p, capital R. And then when I was allocating the RAM, just like that. Okay, so this is saying that it's an array of pointers to rectangles. So people use type def a lot, and I should have been encouraging us to use it more often, but we hadn't gotten to structures much yet. Type defs are best used for structures, I would think. There may be other reasons to use them. I gave you that big num example. Okay, so I'm going to undo those changes so that it goes back to the way it was. Alright, so summary. Oh, is it working for y'all guys? I haven't been checking to make sure that, okay. Summary. If you malloc a structure, you store the resulting address in a pointer. Then to access the elements, you use the hyphen greater than syntax. P hyphen greater than x equals 10. P hyphen greater than y equals 20. Whatever. Right. If we had a structure that contained an x and a y, then that's how we would get a hold of them. In some versions of the compiler, you have to cast the return result of a malloc like this. So if it's a struct called pointer, struct pointer, and it's an array of pointers. No, it's not. It's a single pointer. So I'm just going to call it, no, struct point. Sorry. But oh, fine. Why don't I just use the example that we were using because my brain's breaking down on it. So like rect asterisk PR, a pointer to a rectangle, is equal to malloc, parentheses, size of, parentheses rect, parentheses, in parentheses, in parentheses. But you have to, in other versions, not Microsoft apparently, cast the result like this. You'd think it'd be able to figure it out based on this, but the way compilers work, and I'm not sure how Microsoft is able to get around it, is that all of this is calculated first before it starts to cross the equal sign. Okay, so when calling malloc, you specify the number of bytes, which is usually size of the struct you need, just like we demonstrated here. When the program is done using the data, it needs to free the memory. Otherwise, you may get memory leaks, especially if it's in a loop. Absolutely you will. Memory leaks where the program uses more and more RAM. Unnecessarily. Could even crash the program. You could run it out of RAM. Nowadays computers have huge amount of RAM, but not every computer has a huge amount of RAM. You may be using some teeny tiny computer like a Raspberry Pi or something. I forgot to free the RAM of those things that was in the pointer that were in the pointer array. So I need to come back up here, and now that I'm done printing out all the heights and the widths, did I ever run this to make sure it actually worked? Did I watch the results? One failed. Oh, I opened a multi-line comment and I never closed it. Let's make sure it works. Alright, yeah, it did work. Right, we have 10 rectangles and they each have, you know, different height and width variables. We can make that array as long as we wanted to. If I don't want 10 rectangles, if instead I want 10,000, it's going to take a while to print them. But the computer doesn't care. It gave us, you know, however many bytes it needed. Just lickety split, no problem. I'm going to change that back down to 10. That's a little bit excessive for the demonstration. Okay, so down here, after we're done printing out all, you know, and we could be calculating the array, the area too, right? Int space area. This is right before the printf rect %d height is equal to int space area equals calc underscore area, and we need to pass in one of those memory addresses. Array subscript x, like that. We don't actually have to print the area out, but we could, right? We could tack it on right there before that \n. Why not? So before that \n, area equals %d. And if I'm going to have one more space there, one more placeholder, I better go and actually copy it in. So before the closing parentheses, comma, area. There we go. Right. 10 rectangles. Looks good. Looks good to me. We're done with that RAM. We need to release it. It's going to be one more loop, and it's going to be freeing every element. Now, we can't just free the array because the array is only, you know, 10 items long. That wouldn't even touch all the elements themselves. It wouldn't even touch the rectangles. We need to free every rectangle, so we're going to use a loop yet again. One more copying and pasting of the for statement. And then free parentheses array. I should have named the array Willie so I could say free Willie. Free parentheses array subscript x end subscript end close parentheses end semicolon. I'm going to remove the semicolons just because. All right, I wish we'd gotten to use a couple more lectures with these concepts. I know they probably don't sink in 100% the first time you see it. That's my guess. Hopefully they lodged enough, though, so that when you have to learn them, you can do so. You already know the terminology. You know what a pointer is. A pointer just contains an address, and the computer can use that address to go and change some data. Just like I give you the address of the school, you can go to the school and do something there. If I give a function the address of a rectangle, it can go and find that memory address and treat it as though it were a rectangle variable. So this is kind of neat in a way because we are using just one variable name to hold how many pieces of data? We had 10 rectangles, and each rectangle had both the height and the width. One variable name held 20 different integers. Well, it was an array of references, of pointers to 10 different structures, and each one of those structures has those two members, the height and the width. Alrighty. We all get it working? Are we all happy enough with this? Alright.
I have like 4 areas, I'm not sure why, 3 of them are on my page.
We need our type def. We got type def above it because we're using, yeah, this is one. Just like you have to have your prototype for which you use or something like that. Yep. I just saw a typo, P-R-I-N-G, print. It's one error. Sometimes it gets rid of half the address. Just double click on that one. Is there something funny going on that side percent sign into my percent or something? I'm sorry, I should have. Cool. So what do you use structures for? You create your own complex data type, something that's more than just one variable. What do you use arrays for? To hold sequences of data. You know, they could be simple data types like an array of ints or characters or something, but they can also be an array of structures. Once you move from writing C to C++, You could create arrays of objects that are classes. And what's a class? A class is a structure that has functions added to it. Like this calc area function could actually be part of this structure if we were doing C++, which we were not. And then if you wanted to calculate the area of the structure, you'd just be able to, don't type this, just be able to do something like this. Area is equal to R1 dot calc area. And you remember seeing this syntax a lot when we were doing Python. And you will remember seeing that syntax a lot if you've used Java. Right? This is saying that this is a function that's attached to this variable. The technical name for a function that's part of a class is a method. So this is a method that's part of this variable. And to get that to work, you would have to make that function, that method, a part of the class. So if we were trying to write C++, we would change that word struct to class, and then we would add a calc area method. We're not using C++, so I'm going to delete that. All right, I think we're done. Any questions over this? Are we good enough? We happy? All righty.